We've all been there. The frustration upon knowing that the final answer did not match because of a rather silly mistake. Often, the silly mistake is in the form of a calculation mistake. However, sometimes the mistake is not so silly. Hi, my name is Aditya, and today we're going to look at why Air Canada Flight 143, which took off from Montreal towards Edmonton, had to perform an emergency landing, and what units and dimensions have to do with that. But before that, what is a dimension? A dimension is something which comprises the physical variable. So, for example, length is a dimension of distance, displacement, width, height, deflection, and so on. Typical dimensions are mass, length, time, and temperature. Apart from that, in case of physical processes involving currents, ampere may also be required. So, an entity, the dimension of an entity can be represented as mass to the power A, length to the power B, time to the power C, and temperature to the power D. So, for example, mass small m is m to the power 1, L to the power 0, T to the power 0, and theta to the power 0. Length small l will be m to the power 0, L to the power 1, T to the power 0, theta to the power 0. Time small t will be m to the power 0, L to the power 0, T to the power 1, and theta to the power 0. So we can represent this in a very convenient manner in which we can write down the dimensions capital M, L, T in a columnar fashion, and we can write down the dimensions for mass, length, and time, and it is 100, 010, 000. I have recited them in columnar fashion, and these three M, L, and T are said to be mutually independent, meaning that the dimension of mass cannot be comprised from the dimensions of time and length. Whereas the dimension of velocity can actually be constructed from the dimensions of length and time. But more on this later on. What is a unit? Unit is the quantification of the content of a variable, and that quantification can happen through various means. The unit of length, for example, can be meter, millimeter, feet, inch, yard, and so on. The typical units can be described as SI units, which is the System International, and the BG units, which is the British Gravity System. In fact, the BG system is also not so unique. There can be a whole myriad of units based loosely on the BG units. Let us write down some of the common entities, their dimensions and units. We have already discussed length, mass, and time. I have not written down time over here because time is something which has the same SI and BG units. Length has a SI unit of meter and a BG unit of feet. So 1 foot is equal to 0.3048 meter. Mass has an SI unit of kilogram and a BG unit of slug. So 1 slug is 14.59 kilogram. And you may have come across the unit pound. So that is the foot pound system, but it's slightly different from a BG system. Temperature in SI units is given as Kelvin, and sometimes it is also written as degree Celsius, no problem. In the BG units, it's represented in terms of Rankine, R. So 1 Kelvin is 1.8 Rankine. So now area will have the dimension of length squared, because area is length times length. So it will have a dimension of m to the power 0 because it has no mass component, L squared because it is length multiplied by length, no component of time meaning t to the power 0, and no component of temperature meaning theta to the power 0. The SI unit of area is meter square, whereas the BG unit is feet squared. And I request you to find out the conversion factor of 1 meter square to feet square. Proceeding, the unit of velocity in SI is meter per second, whereas in BG system it will be feet per second. And the dimension, quite naturally, because velocity is a length per unit time, that is the rate of change of distance per unit time, and so the dimension will have L to the power 1 and T to the power minus 1. The other exponents will be 0. Acceleration, again it is the rate of change of velocity or the second derivative of distance. So it is L squared T to the L to the power 1 T to the power minus 2, and the unit in SI is meter per second square and the BG unit is feet per second square. Force is mass times acceleration. So whatever dimension you have for acceleration, that will be multiplied by mass. So the dimension for force is m to the power 1, L to the power 1, T to the power minus 2 and theta to the power 0. The SI unit is famously Newton, whereas the BG unit is pound force or lbf. The unit lbf refers to the gravitational force acting on an object which has a mass of 1 pound. So essentially it is 1 pound multiplied by 1 g, where g is the acceleration due to gravity, and g has the unit 9.8 meter per second square, which you should convert it into BG units. Alternately, you can also convert pound to kilogram, where 1 pound is 0.454 kilogram, and we'll see one small calculation towards the end of this session. So I request you to work out all the other units. I've written them down in this table. I request you to find out the conversion factors and the BG units. It is a simple yet effective exercise to get everyone through the rounds, through the motion. Some useful fluid properties. Pressure. Pressure is defined as the force acting normally to a given area. In the case of a flat area, it is the force acting normal to the flat area. In the case of a sphere, it is the area acting normal to the surface of the sphere. Pressure has the unit Pascal and it is force per meter square. So with the help of this definition, which is a very crude definition to be honest, you should be in a position to determine what the dimensions of pressure are, what the units in SI system, it's obviously Pascal as I've mentioned over here, but what should be the BG units in terms of pound force and feet. Density is defined as the mass per unit volume, and the SI unit of density is kg per meter cubed. The next important property is fluid viscosity. Imagine an element ABCD as shown in the figure. The top surface, that is segment BC, is acted upon by a shear, shown in this case by the red arrow. Because of this shear, the fluid element deforms continuously to a shape A prime, B prime, C prime, D prime. The angle that the segments AB and CD make with the horizontal line AD prime, or rather AD, is delta theta. So the shear strain in this case is delta theta, whereas the applied shear is tau. Now it has been found that there exists a linear relationship between the stress and the rate of change of angle of the fluid element. That is, tau is proportional to del theta del t. Now point B moving relative to point A is what causes deformation. In this case, if A and B were to have the same velocity, there would be no relative motion in the x direction between A and B, and hence there would be no change in angle. But the fact is that point B moves faster than point A. That is to say, if point A has a velocity u and if point B has a velocity u plus delta u, then point B has a relative velocity of delta u with respect to point A. In time t, therefore, point B moves to point B prime and the distance is delta u multiplied by delta t. The angle delta theta can be related to the displacement of point B and the distance of point B from point A, such that tan of delta theta is equal to length BB prime divided by length AB, which is delta u multiplied by delta t divided by delta y. For an infinitesimal change in time, delta theta can be approximated as tan delta theta, and therefore delta theta divided by delta t is equal to delta u by delta y. Now Newton's law of viscosity, which we have previously mentioned also, that the stress is linearly proportional to the rate of change of the angle between the vertical, implies that tau is also proportional to delta u by delta y, as we have just shown previously, and thus tau is proportional to del u by del y in the limit time tends to 0, rather the delta t tends to 0. So in the limit delta t tends to 0, delta u by delta y is also equal to del u by del y. So tau, which is the shear stress, is proportional to del u del y, meaning tau is equal to some constant times del u del y. And this is a relationship, a linear relationship between the shear stress and the velocity gradient, because in this case the velocity gradient is del u upon del y. And this linear relationship, the constant in this linear relationship, is called as the viscosity, and this was first proposed by Newton. So back in the day of Newton, the analysis used to consider typically that the response of a fluid or even a solid is linear to the force applied on it. So Hooke's law is one such example in which the stress and the strain are linearly related. So viscosity is therefore having the units of stress divided by the velocity gradient, which is to say the dimension of viscosity is m L to the power minus 1 t to the power minus 1 theta tends to raised to the power 0, and the unit is kg per meter per second, which is nothing but Pascal second. The viscosity depends strongly on temperature, and this is quite an important physical parameter because, for example, in a motorcycle engine or any engine, there is a certain amount of lubricating oil that exists in the crankcase. When the engine is running, the engine starts becoming hot, and so the lubricating properties will strongly start to depend on how the viscosity starts changing with temperature. Actually, for degraded oils, for oils which have not been changed for quite a while, the viscosity does not appropriately change with temperature, leading to inefficient performance of the engine, which is one of the reasons why engine manufacturers will ask you to replace engine oil now and then. In fact, this is the reason why there are various grades of engine oil. Various grades of engine oil have various varying degrees by which the viscosity varies with each 100-degree rise in temperature, for example. These kind of graduations are done by the SAE, which is the Society for Automobile Engineers. But anyway, the temperature dependency of viscosity for liquids differs from that of gases. So in the case of liquids, as temperature increases, the fluid starts to become less and less viscous. However, for the case of gases, as the temperature increases, the viscosity also increases. Now we can understand that in the case of fluids, if the temperature increases, the intermolecular forces between liquid molecules reduces, which is to say the temperature allows the molecules to overcome the intermolecular bonding. That is why the fluid starts becoming more loose. That is to say the viscosity of the fluid reduces. But what is the situation with gases? The viscosity in the case of gases manifests because of the collisions between the gas. So the more gas molecules collide with each other, the more you will perceive that the gas is more viscous, because in the end viscosity is sort of a dissipation. So in the case of gases, if the temperature increases, the number of collisions between the gas molecules will also start to increase, as a result of which we will see that as temperature increases, more and more gas molecules are colliding, more energy is being dissipated, and hence the manifestation, macroscopic manifestation of this will be that as the temperature increases, the viscosity of gases also increases. Now coming back to the original question, what was the reason behind Air Canada Flight 143 performing an emergency landing in Gimli, Canada? In 1993, Air Canada was still working with imperial units, whereas the new shipment of Boeing 767s at that time were shipped with metric units. The distance between Montreal to Edmonton was such that the fuel requirement was 22,300 kilograms. The pilot had measured prior to the flight that the tanks already contained 7,682 liters of fuel with the help of a float stick, which is an analog device. So now the question was, how much fuel does the aircraft need? In order to find that, we have to first convert, or rather the pilots had to first convert the fuel volume to mass, subtract the available mass from 22,300 kilogram. This is the required mass. This required mass can be then converted into volume. The useful parameter is that the density of fuel is 0.803 kilogram per liter or 803 kilogram per meter cube. So let us do this calculation. 7,682 liters translates to a total mass of 6,169 kilogram. This is obtained by multiplying the volume by the density as shown in the first step. So now 6,169 kilogram of fuel already exists, which we can subtract from 22,300 kilograms of the fuel required, which yields 16,131 kilogram of fuel. Now 16,131 kilogram of fuel is what is required, but we have to report this mass in liters. So 16,131 kilogram multiplied by 1 upon 803 kg per liter. So the kg gets cancelled and we obtain 20,088 liters. So essentially 20,088 liters of fuel should have been filled into the aircraft. But what actually happened? Because Air Canada used imperial units, the density of fuel was 0.803 kilogram per liter multiplied by 2.2 pounds per liter. So 0.803 multiplied by 2.2 is 1.77. The 2.2 comes from the conversion of kilogram to pound, because 1 kilogram is 2.2 pounds. So it yields a density of fuel as 1.77 pound per liter. So what did the actual calculation of the pilot suggest? The pilot wrote down 7,682 liters multiplied by 1.77 pound per liter, which comes out to be 13,597 pounds. The crew interpreted this poundage as kilogram instead of pound because they thought whatever the pilot is reporting should be in kilogram rather than pound. So now, merrily working on, he thought 13,597 kilograms are already there. So he subtracted that amount from 22,300 kilogram, yielding a mass of 8,703 kilogram. Then he proceeded to convert 8,703 kilogram to liters. So then he divided 8,703 kilograms by the density, which is 1.77 pound per liter, and incorrectly resulting in a calculation of 4,917 liters. So the fuel that was actually required was 20,088 liters, but because of the confusion in units, the amount of fuel that was filled was only 4,917 liters, which means that the aircraft flew with a net deficit of 19,171 liters. And this confusion arose solely because of the mismatch between the units which were already in place in Air Canada, which is imperial, that is pound per liter kind of unit, but the new Boeing 767s were being supplied with panels, and it was instructed to the pilots that they should start using kilograms. Both the pilots calculated the same amount of fuel required because instead of using kilogram per liter as the density, they actually used kilogram per liter, but instead of using the actual unit of 0.803 kilogram per liter, they used the density as 1.77 kilogram per liter instead of 1.77 pound per liter. All this mumbo jumbo calculation led to a very catastrophic calculation in which a very small fraction of the fuel was actually filled, as a result of which the plane started running low on fuel immediately after takeoff, and it had to do an emergency landing. And the emergency landing was done in which all the engines of the aircraft were non-functional because none of them had any fuel to run on, and hence the pilot had to glide the aeroplane, and hence this incident is also called as the Gimli glider incident. A similar incident also happened with the Mars Climate Orbiter. In 1999, the orbiter was lost due to a software issue because one of the pieces of software produced output in foot-pound seconds, but the other piece of software of the orbiter expected the output in Newton seconds. So Newton seconds is a unit of impulse. Okay. So when you have to correct the trajectory of a satellite, you have to use various thrusters, and this is how you measure. So Lockheed Martin was supplying everything in foot-pound seconds, whereas NASA expected everything in Newton seconds. So what was the factor of error that was being propagated because of this unit mismatch? Let us find out. 1 pound force is equal to 1 pound multiplied by 1 g. So 1 pound is actually 1 upon 2.2 kilogram. So when you multiply this by 1 g, that is 1 gravity, you have multiplication by 9.8 meter per second square. So if you do the calculation, you obtain 4.45 kg meter per second square, which is nothing but 4.45 Newton. So 1 pound force is equal to 4.45 Newton. So in the first system, if the output is 1 foot-pound second, system 2, which expects an input as Newton second, would have interpreted 1 foot-pound second as actually 1 Newton second, thereby underestimating the amount of impulse required by a factor of 4.45. And this underestimation led to the fact that the orbiter bounced violently off the atmosphere of Mars and was lost, resulting in a rather sizable amount of loss to the tune of hundreds of millions of dollars. So, to conclude, units and dimensions form the very basic blocks of any kind of analysis, not just fluid mechanics. And it should be kept in mind that yes, while steps and all do matter, arriving at a precise final answer is of the paramount importance if one is to ever make something which is valuable for mankind. There is no scope for silly mistakes in real engineering. People have witnessed such drastic events, catastrophic events, which have happened due to extremely trivial calculation mistakes. So I hope you will take into cognizance the two examples that I have given in this particular session. With this, we conclude this particular session, and I'll be back with a new lecture next time. Thanks for watching. Goodbye.